Well, hello there. Today we're talking about chemistry and specifically the periodic table and how atoms work. So, looking at the picture here, you see a crude diagram of an atom. Things are much more complicated than this in reality, but this little simple picture, simple model that we'll talk about will do plenty for what we're trying to do here. So, notice that I've got three kinds of dots here, right? These blue ones are called protons, and they have a positive charge. They're in the middle. They live in what we call the nucleus, the center of the atom. These purple dots here are called neutrons. They have no charge. They're not positive, they're not negative, they're neutral. And they live with the protons in the middle. And then zipping around the outside, almost in this picture, in this model, like planets around the sun or something, I've got these red dots, the electrons, and they have a negative charge. Three different kinds of particles: positively charged particles, negatively charged particles, and neutral particles. The positive and the negative charges, the protons and electrons, have virtually the same charge, but one's positive, one's negative. The unit here is called coulombs, or capital C for abbreviation. We've seen this back in test 2 material. Remember when we were calculating the force between charges? But 1.6 times 10 to the negative 19 coulombs. Positive if it's proton, negative if it's electron. Again, neutrons have no charge, so that's a big zero there. On the mass, the protons and the neutrons are very nearly identical. 1.673 times 10 to the negative 27 versus 1.675 times 10 to the negative 27. This negative 27, of course, means that you need to put 26 zeros in front of that 1 and move the decimal place 27 times that way. So it would be 0.0001675. Okay? For all practical purposes, the mass of the electron here is essentially zero. You see that it's about 1,000 times smaller than the mass of the proton. So we just kind of sweep it under the rug and don't worry about it. The proton has a mass of 1 AMU, atomic mass unit. The neutron also has a mass of 1 atomic unit. We say that the electron has 0. This is an interesting model. It's a worthy question how we arrived at that point, why we believe it looks like this. And I'll tell you right away, there was a guy named Rutherford. And Rutherford worked all this out from an experiment that a couple of his students did at his direction. The model before what we use now with the positive and neutral charges in the nucleus was called the plum pudding model. And I don't think you've ever had plum pudding. I certainly haven't. But it's a goopy, sticky, squishy kind of thing with plums stuck in all over. They eat it in England. And looks something like you see here, I guess. I've never seen one. I kind of compare it to either raisin bread or chocolate chip cookies or something where you have all of the mass there, and then the protons are kind of stuck wherever you want them, kind of randomly distributed in the mix. Okay, so they knew that there were positive charges, negative charges. They kind of in their mind they had this model. Well, it's like a big squishy plum pudding. Rutherford's experiment was to send his graduate students down the hall, give them an alpha source. This is an alpha particle. Remember the radiation we talked about with the alpha particles? That's a positively charged particle. And so he said, I want you to shoot some alpha particles, to stream off some alpha particles, and make them hit a gold foil here, kind of like aluminum foil, but much, much thinner. This had been pressed really flat, a couple of atoms wide or something. And so they go down the hall. They do this. He gives them a little screen that they can slide back and forth in the circular arc right here. And the screen is painted with phosphor, so it creates a little flash every time an alpha particle hits it. And so they can sit there and count how many times it flashes and know how many alpha particles are coming through right there. And the expectation is that these alpha particles, being so small relative to the atom, would just pretty much sail through it. almost like if you took a chocolate chip cookie and shot it with a BB gun, right? A BB gun, or even a rifle, the bullet would just go straight through it. Wouldn't even pay attention to it. Wouldn't be deflected, wouldn't be bent left or right or backwards or anything like that. What they came down the hall with the results back to Rutherford was that sometimes these things scatter at very large angles, back scattering. You fire this little bitty alpha particle here, and it can get bent straight back on its path towards its source, or off at some large angle like you see here. It didn't fit the model, and so Rutherford had to sit down and say, well, what's going on here? He knew that the model must be flawed. He came up with a new one that looks like the picture we just had, and he said, let's put all the positive charge in the center of the atom. That way, when my positively charged alpha particle comes at the nucleus, that positive to positive repulsion there, the Coulombic repulsion, would be enough to drive it back. Whereas if the positive charge was scattered everywhere, there wouldn't be enough. And so of necessity, we now put all of the positive charge in the middle. Since the days of Rutherford in the 20s or 30s, whenever that was, we have learned a lot more about the atom, and so we know he was right. But that was a pretty good guess and a pretty good experiment that led people to a better understanding of atoms. That understanding today is encapsulated in what we call the periodic table. This is a single sheet of paper that gives us an awful lot of information about stuff, about the stuff of the universe. So here you see this table. You've seen it before in middle school, high school, somewhere. And it's made up of rows, and it's got columns. There's a reason that these things are in rows and columns. There's a reason that there's a big hole here in the middle. And so let's say a word about that. First of all, the columns are important because everything in the column, in a single column, would have similar chemical properties. Coming down this first column, I've got hydrogen, lithium, sodium, potassium. These guys here are very reactive, and they will react with almost anything. These guys on the end over here, helium, neon, argon, krypton, they're not going to make a deal with anybody. They will not undergo any kind of chemical reaction at all. Anything that's in this column here will mix very nicely with anything that's in this column here. So there's lots of chemical properties and similarities between things that are in the same column. One more example right here. Number 29 is Cu for copper. 47 right below it is Ag, or silver. And right below that, 79 Au is gold. So copper, silver, gold, straight down the list. Those are very similar metals, right? We can beat on them and make jewelry. We can make coins. They're all excellent electrical conductors. They have similar thermal properties. They can be melted and poured into, all the way down the list. These are similar metals, and so they go into the same column. If I zoom in on a particular box here, and we've done that with carbon here, you can see there's a lot of information about each individual atom as well. The most important thing is how many protons there are. The number of protons is called the atomic number, and that's that big number at the top here. You see that carbon has 6 protons. The atomic number is 6, so there have to be 6 protons in the nucleus. Right here next to it, boron has 5. Beryllium only has 4 protons in the nucleus. That makes it fundamentally different than carbon. Makes it different than neon and gold. That's the distinguishing feature here between all the different kinds of stuff that we know about. So here's hydrogen. It only has 1 proton. The biggest one on this table, 109. I don't even know what that stands for, but it has 109 protons in there. So you can look at that atomic number and immediately tell how many protons there are. Incidentally, if an atom has 6 protons, then it should also have 6 electrons. That number is generally balanced When it's not balanced, we refer to it as an ion. An ion has a different number of protons and electrons. It's electrically unbalanced, if you will, but generally these things are balanced. So if I have 6 protons, I'm expecting there to be 6 electrons zipping around the outside. And indeed, that's what we find. This number is the number of protons. It's also the number of electrons, unless something weird's going on. There is a symbol C. We just don't want to write carbon all day long, so we just say, well, let's let C be the symbol for carbon. Some of these symbols come from Latin. AU for gold, Rm. You know, some of them come from other sources. Some of them are named for people. There's a Rutherfordium or something. I can't remember exactly how. I don't have my full-size chart here, but you know, some of them are named for places. There's an Americium with name for America. There's a I think there's a Californium or something. Different places are remembered for, you know, pretty much if you find it, you get to name it. So there's a council that debates over it for a while, but in the end, you've got a pretty good shot at getting your name put on it. Let me tell you about the electron shells. We said that they should be the same as the number of protons, but let me give you a little more information. There are shells of electrons, and there are only so many electrons in each shell. They like to fill from the inside and work their way out, and they want to have a full outer shell. Let's kind of go through those again. Right here you see that there is a shell around the nucleus. You see that there are only 2 electrons in that shell. That's because you can only put 2 electrons in that shell. So if you had hydrogen, that would have 1 proton, 1 electron. That 1 electron would go right here. If you had helium, that'd be 2 protons in the nucleus, and then 2 electrons in the first shell. When you go to number 3, lithium, you'd have 3 protons. You got to have 3 electrons. You put the first one here, you put the second one there. The third one's got to go into the next shell. There's no more room here, right? So it's going to go somewhere on this shell. It's almost like when you walk into a classroom and there's 8 seats in the front row and 8 seats on the back row, right? And the front row is filled up. You got to go to the next row, right? You can't squeeze in somehow. There's only so much room. Students like to sit on the back of the classroom. Electrons like to come down to the front. They are excellent students, right? Why? Well, this is a big positive charge right here, the nucleus, and the electrons are negative, right? So there's an attraction. They're attracted to sit as close as they can. So these inner shells are filled first. This is the kicker. This is the funny one. The atom wants to have a full outer shell. I can't really tell you why. I think it has something to do with energy levels and balance. Have you ever tried to carry one heavy suitcase? It doesn't work too well, does it? It's much easier to balance that out and carry it in both hands. Even having 2 heavy suitcases is better than having 1 heavy suitcase. So something about the balance. I've only got 2 hands. You know, if I had 8 here, I guess I'd know a little bit more about that. But it wants to be balanced, and so it finds a way to do that. And we'll talk about that in the next video. Right here, I wanted to go back to the periodic table. As we look at this thing, we said that carbon has 6 protons. It's also going to have 6 electrons. We start thinking about how it's going to fill those. I need to count to 6. I'm going to put the first one in the first shell. There's room for the second one in the first shell, but at that point this one is full. So I got to step out to the outside. I've already used 2 out of 6. So my other 1, 2, 3, 4 have to go in the second shell. And you can see that there's still plenty of room over here. I'd have 1, 2, 3, 4 more that are empty that could be there. So carbon does not have a full outer shell. It would like to have 4 more seats filled. As it is, it's got 4 full. It's got 4 openings there, 4 vacancies. So carbon's not happy. And what carbon will do is make a chemical reaction with another element to gain those 4 electrons in the outer shell. We'll talk more about that in the next video. Hydrogen here, or lithium, or sodium. Let's think about sodium. That's number 11. We said all of these are very reactive. I've got, if I count to 11, I'd put 1, 2 in the first shell. I can put 8 in the next shell, 3, 4, 5, 6, 7, 8, 9, 10. I'm up to 10 now. I've got 1 electron left, and he's got to go in the third shell, and that just ticks sodium off. He's got 1 guy hanging out there. If he could get rid of that 1 electron, he'd be to a full outer shell, and he'd be happy as a clam. As it is, he's pretty upset. He's unbalanced. Look at neon here, though. Neon has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Neon has a full outer shell. Neon's not going to make a deal with anybody. He's happy. He's got that full outer shell. He's like, leave me alone. But these guys, they want to get rid of 1 electron. These guys want to get rid of 2 electrons. Pretty much the rows of the periodic table represent filling up the shells. Right here on the first row, see how there's 2 boxes? It's because I got 2 electrons that I can put in there. Hydrogen puts 1, helium over here number 2, 1, 2. When I go up to lithium number 3, there's 1, 2, and the third one's got to go out here somewhere. So there's only 1 in the outer shell. I'm in the first column there. Everything here has 1 electron in the first in the outermost shell. These guys all have 2 electrons in the outermost shell. Gets a little complicated in here, but these guys are all full. These guys are all 1 short. They would like to have 1 more electron. So there are a lot of deals that we'll be looking at where these guys and these guys will get together. And again, the columns represent similar chemical properties. The rows represent filling the electron shells. And we'll talk more about the chemical reactions next time. Thank you.